for inviting us all here, and it's great to be in Copenhagen. Disclaimer, as I'm sure is the case for many of you, it's like 3 a.m. Eastern time for me, so please, my brain's functioning properly. I'm just gonna beg forgiveness and see what we can do. So anyway, as Dennis was saying, there are tutorials, and then some of the later talks will be more advanced. So this is the first talk, and it's also a tutorial. So my intention for this was basically to have it be absolute beginners. So that means many of you will be bored. Hopefully some people get something. Okay, right, so others. Okay.
That one should be better.
This is what I'm using. Yeah.
But there's no hello.
It's okay. Okay. So we'll come to the rest of you, but for the meantime, I'll write some really boring stuff here. So standing convention, working over field of characteristic 0, and so mainly just for kind of simplicity, assume it's algebraic and closed. So sort of first main character will be a connected reductive group. And I said, I guess this one is the talk for beginners, so feel free to assume this is GLN and kind of make comments at various times about what happens when G is GLN. Okay, so the next guy that I want to introduce is the classifying stack of G. And so again, this talk is my intended audience here is people that maybe have some background in algebraic geometry, maybe you're a grad student, but haven't thought a lot about algebraic stacks, so I'll kind of try to be general about this aspect of the theory because, well, we'll ramp up a bit later, so might as well go slow now. So I'll write point mod G for classifying stack. Of the group G. So first of all, what is this thing? Well, as a stack, it's classified by its points. So if S is an affine scheme, so S will kind of always denote a test affine scheme. Specify this gadget as a stack, I just need to specify maps into it. And so these will be it's all locally trivial. So locally trivial and some suitable topology, principal G bundles. On S. And from now on, I'll probably be a bit loose about this. And just, when I say principal G bundles, I mean locally trivial. Yeah. Perfect. Thank you. All right. So this is the first thing appearing. It's not an algebraic variety, but it's kind of the simplest possible stack. You're supposed to think about it as somehow a disembodied point that has G as through homomorphisms and kind of nothing else there. So for example, classifying stack of GLN classifies vector bundles of rank n. So what do you think about this case? You're not experienced in any theory. Oh yeah, also throughout, feel free to interrupt and ask questions, but especially in this talk, I mean, please interrupt me if I say anything that is confusing. Okay, so then the next main character is X. X is going to be a smooth, connected, I guess, projective curve. Okay. Okay, so K is complex numbers. This is like a compact Riemann surface. And then finally, we come to Bun G. So the most concise way to say the definition of Bun G is, as a stack, is that it's the space of maps from X into the classifying stack at one Bun G. It's just an efficient way to write it explicitly. Points are principal G bundles. So a family of points upon G parameterized by a test scheme S would be a G bundle upon S times X. Okay. So far so good. So there's Bun G. That's our definition. What is this thing? Well, it's some kind of algebra geometric object. So we kind of go into more detail about what exactly kind of the thing it is. Okay, so the first kind of main fact about it, I probably won't prove very many things in this talk, so most things will be try to give some references. So this just defines an abstract as an abstract stack, right? For every affine scheme I specified. Oh, and I should say this is being very loose with my notation here, but since this is the talk for beginners, I should say this is a groupoid, and already this was the case up here, right? So when I write these curly braces, I'm being sloppy with the notation. It's not just a set, but it's actually a groupoid. I know what it means to give an isomorphism of principal G bundles, and so I'm specifying this thing not just as a functor valued in sets, but as a functor valued in groupoids. So this will always kind of be implicit, right? When I write some data, I mean, those will be objects, and then the morphisms will be isomorphisms of such data. Okay. So this specifies Bun G as an abstract functor, but in fact it has some nicer properties. So Bun G is called an algebraic stack, which is locally a finite type over the ground field. And we say what this means a bit more precisely. Okay, so so you go and look in, I don't know, what's the reference for this? Lamont and Murray Bailey are one of these references on algebraic stacks. There's some condition on the diagonal, okay? It's supposed to be somehow nice. And what happens for Bun G, in fact, it's a particularly nice kind of stack. And the diagonal is actually an affine morphism. Right? Meaning if I take some affine scheme mapping here and base change, I get an affine scheme. So this is, again, it's a particularly nice type of algebraic stack. In general, algebraic stack means the diagonal is representable by an algebraic space or something like this. In this case, the diagonal is actually an affine scheme, so it's a particularly nice kind of stack. And this is a condition that looks more familiar if you're used to differential geometry, right? So there's some kind of chart, there's some kind of coordinate atlas. So we say there exists a scheme U, locally a finite type. Okay. And smooth surjective morphism from U to Bun G. Okay. So this is what we would call an atlas, sort of by analogy with differential geometry. Now, I mean, maybe unlike differential geometry, we kind of rarely, if ever, actually kind of work with such an atlas. It's useful to know that it exists, but there's sort of other things that are which cover Bun G that'll be more useful that we'll see shortly. But it's good to know that people can exist abstractly. If you want to read more about this, I I think kind of the standard reference is some notes by Sorger and moduli principal G bundles. And there's also some notes from Dennis's 2009 seminar, which are a good reference in general for a lot of the background material. If you haven't looked at this before, go on Dennis's website and look for the link to the seminar from 2009, and there's many great notes there, including some notes by Dennis where he proves this representability result. But basically the idea is you first prove this for G being GLN. Okay. Vector bundles of fixed rank form a stack, and this somehow reduces to classical representability results for quote schemes and this sort of thing. And then you further, then you reduce the general case. You embed your arbitrary G into GLN and prove the general case by reducing GLN. Questions so far? Great. Okay, so somehow so far this still doesn't tell you so much how you should maybe visualize Bun G or something. It's just saying it's not too horrible. One thing that's useful to point out right away is that Bun G is actually smooth. It's an algebraic stack. And here maybe I will actually kind of sketch the proof because I think it's some useful ideas in here that probably will also come up in Dina's talk. So now we see this, and it's interesting because somehow this is, as you'll see in a very precise sense, Bun G is smooth because X is a curve, because X is one dimensional. So, okay, so this will be a little bit animated. It's a sketch. So, an algebraic stack, locally finite type. So, in classical algebraic geometry, if I have a scheme of finite type or an algebraic variety or something, it has a tangent sheaf, right? And we can detect smoothness as a property of this tangent sheaf. Basically, condition is that it's a vector bundle, right? So for an algebraic stack, you can no longer, you don't want to talk about the tangent sheaf, rather there's a complex. So some general machinery tells us that this has a tangent complex. So for at least kind of for sufficiently nice stacks, is actually a perfect complex. Meaning it's a bounded complex of vector bundles. Okay, so explicitly this means for every affine scheme mapping to, in this case, Bun G, right? The tangent, the kind of fiber of the tangent complex at that point will be some perfect complex on the affine scheme. And we can, analogously to the classical case that I just said, you can say what it means for an algebraic stack to be smooth in terms of its tangent complex. And the condition is as follows. So such a stack is smooth if and only if its tangent complex is connective. Okay, so this is some terminology from, I think, probably mostly used by algebraic topologists. Let me just say what it means. It means concentrated in non-positive homological degrees. Okay, so in general, it's some bounded complex. Maybe it has cohomology in degree 0, and a priori, this can go off to the right and to the left, and smooth means it only goes off to the left. Okay, and so then for what happens for Bun G in particular. So again, I have to weasel here just for reasons of time, but if you haven't seen this before, you're curious, please ask me about it. So a standard calculation shows that in this case, the tangent complex of Bun G can be described explicitly. So I'll describe its fiber at a fixed G bundle, right? So I guess I should say sort of the fiber of the tangent complex, which, like I said, will be a perfect complex on whatever test scheme parameterizes P. And this is following. So you take the G bundle PG to P, you can attach a vector bundle on X, which is called the adjoint bundle, right? So, okay, so as usual, the German G is the Lie algebra of G. And this it's a representation of G via the adjoint action. And so there's this associated bundle construction to PG, and this representation, I can attach a vector bundle on X. And I take its derived global sections and then shift by 1. Okay, so kind of very classical arguments from deformation theory tell us to form a G bundle. The deformations are exactly kind of controlled by this complex. Okay. And now, as I say, X is a curve. So the point is sort of, if I have any coherent sheaf whatsoever on X, right? Here's the eraser. I can use the sponge. It's fine.
Sorry, one more question.
Please.
The logical shift, like which direction is the
Great question. Yeah, because it's very confusing, right? So this R gamma a priori is concentrated in positive cohomological degrees, right? It's in degree 0 and off to the right. And so then when I shift it, it'll be the lowest cohomology R0 will be in cohomological degree -1 going off to the right. Okay. But now, in fact, what happens, right, is for X being a curve. I hope the waving of my hands made that more clear.
In deformation theory, deformation is controlled by H1.
Correct, yeah.
So then H1 is at the
R1 gamma sits in cohomological degree 0. Thank you. Yeah. H1 sits in cohomological degree 0 here. Okay, so for any coherent sheaf F on X, because F is a curve, right, the cohomology will vanish for any I strictly greater than 1, because X is one-dimensional. Right? Most basic vanishing result for coherent cohomology. And therefore, exactly this condition is satisfied, right? How did I write this? So this exactly tells us in terms of this criterion that Bun G is smooth. Okay. Question so far? I think this is a useful calculation to go through because we'll kind of see like what happens for local systems and it's different. Yeah.
Yeah, I have a question. But Bun G was kind of sort of the mapping thing. Yeah, is there a relationship between that and the performance of the tangent?
That's exactly what I was saying with this standard calculation thing, right? So yes, for anything that's kind of written as a mapping complex in some suitable generality, you can write a formula for its tangent complex in this form. So that's exactly what I'm alluding to. So if you're more curious about that, please ask me after the talk. But yeah, that's a good point. That's precisely because it's written as a mapping stack that such a formula is good. Okay. Any other questions? I feel that I'm going very slow, but I think that's good. Like my brain, it's perfect. Okay, so all right. And an important remark here that would be used is that none of the above use the fact that G is reductive. right? I just simply didn't use it. So any of this would work for G being an arbitrary algebraic group, and indeed we'll use this. For example, G has many interesting subgroups which are not themselves reductive, such as Borel subgroups and parabolic subgroups and so on, and we'll definitely consider Bun G in such cases. Okay, and now I'll say this as an aside. Somehow it's an important point, but it's maybe not something we'll kind of use in a literal sense, but it's very important context to keep in mind. And that is for G reductive, I will say something specific in the reductive case now. Bun G is never quasi-compact. Okay, probably there'll be someone that is annoying in the audience, and I should say like non-trivial. Is it going to be you here? Okay, so all right. So yeah, so for reductive non-trivial G, Bun G is never quasi-compact. Okay, and this is kind of in an interesting way. So let me say first, the kind of less interesting case of this is that let's say G is the multiplicative group GM. So the moduli stack of GM bundles parameterizes line bundles on X. This is also known as the Picard stack of X. Okay, it's a familiar object from classical algebraic geometry where you would often kind of rigidify it and think about the Picard scheme, but this thing looks like the Picard scheme times a copy of the classifying stack of GM, which parameterizes the automorphisms of a line bundle. And the connected components of this stack are parameterized by integers via the degree map, right? So we have this discrete invariant that controls the connected component. And so in particular, we see that it's not quasi-compact for kind of a boring reason, which is that there are infinitely many connected components. Okay. But more interesting would be the non-abelian case. So for G non-abelian, even the connected components themselves are not quasi-compact. And this is it's kind of an exotic thing. I mean, I suppose this is technically possible for a scheme, but it kind of doesn't often happen in practice. But there are many stacks, well, Bun G in particular, which are very natural and have this kind of feature. So you should think it's sort of more characteristic of this type of stack geometry. Again, it's a bit hard to imagine from the perspective of classical algebraic geometry. If you're used to thinking about varieties, of course, this never happens. Like variety, if it's connected, is quasi-compact. Let me just give like a very coarse kind of demonstration of this. So the reason for this is, let's say, for Bun GL2, so moduli of rank 2 vector bundles, we have the following picture. So we can consider the trivial rank 2 vector bundle, okay? And this actually specializes to the rank 2 vector bundle O of 1 plus O of minus 1. Let me just say, what I'm say here. Let me do sort of for simplicity just P1, but it's not hard to generalize this to an arbitrary curve. So I'm just assuming it's the projected line, so I can write like O of 1 and things like that. But you can imagine in general, just take O of a point X or something.
Or you can also just have your curve P1 and pull that.
Correct. Yeah. So this is illustrative of the general case, right? So what I mean by this wiggly arrow here is that this point specializes to this point. So this point, this is a K point of Bun G, and in fact, it's contained in the closure of this K point. Also kind of a weird, very characteristically stacking type of behavior, right? But in any case, what happens is that then this point further specializes to O of 2 plus O of minus 2, and so on and so forth. And this process goes on forever. And so you see this demonstrates that PGL2 is not compact because we have this kind of infinite sequence of points. It's just specializing further and further.
Right,
No, not on the spot. But yeah, no, it's you can write something very explicit. So yeah, please do it as an exercise. If you get stuck, then ask someone, not necessarily me.
Correct specialization.
Yes.
Look, can I just say out loud?
Please do.
Okay, but the way to do the exercise is there's a one-dimensional space of extensions of O1 by O minus 1 by seriality. And you can check that there's a unique non-split extension. The exercise is to see that non-split extension is O plus O. And then you can degenerate that down by pair scaling down to get O down to get the split extension. And that's the way this specialization.
Thank you. First specialization. Fantastic. All right. So if I try to do anything that I didn't particularly think about before, I would fail. So, all right. Any questions so far? I'm gonna kind of shift gears. Yes.
Please. Just want to say, so thank you for your talk. Because you comparison, like, I mean, I know that this is side, it's not jail, it's not.
Correct. So I'm saying for G non-abelian, the connected components of Bun G are not quasi-compact. So this sequence of specializations takes place in the connected component of the identity. Never quasi-compact. Yeah. Right. Precisely. So yeah. So or another way of saying it is you can think about this as taking place in Bun SL2, right? Which is in fact isomorphic to the connected component of the identity in Bun G. Yeah.
So it's the arrow up if the thing on the left, if there's specialization of thing on the right.
Was I saying when specialization backwards from what you use that? Yeah.
So the arrow is specialization or generalization.
Specialized, like
You know,
the thing on the right of the arrow is contained in the closure of the thing on the left.
you know,
Yeah. Okay. Other questions? Great time to ask questions now. Thanks. Okay. And again, if you're not used to this, it is supposed to be kind of exotic. And I mean, you should think these are points. In fact, so what happens for P1, for any reductive group G, is that the K points are actually discretely parameterized. So there's a discrete collection of K points. Each of them has some group of automorphisms. And you should think, so it's a bunch of classifying stacks that are somehow glued together in a non-trivial way. And there's infinitely many of them. So there's some sort of stratification where the dimensions of the strata are kind of escaping off to minus infinity. Very, bizarre from a classical perspective, kind of stacking geometry. And for those that think about such things, you're kind of arithmetically inclined. This is supposed to be kind of analogous to the fact that a fundamental domain in the theory of automorphic forms is non-compact. These things are very closely analogous. Okay, if there's no more questions, I'll move on to the next topic, which is the Hecke action. All right, so for this discussion, I'm going to fix single K point of my curve x, little x, and later it's going to be very important to allow this point to vary and to allow multiple points and so on. But I think for probably my entire talk, I'll stick to the case where x is just a single fixed point of the curve. So just kind of set the stage. Suppose for a moment that we work in a case where K is actually the complex numbers. And in this case, we have the complex analytic topology available to us. Okay, so in this case, I can describe a G bundle. And in this case, X is actually like a classical compact Riemann surface. That I can describe a G bundle by some particular Bun data. And as follows. So first piece of data is the G bundle. Let me call it P prime. I'll say P for the actual bundle on X. So P prime is a G bundle on a small disk in the analytic. So a small analytic disk centered at X. Right. The second piece of data is a G bundle P prime prime on the complement of point little x in the Riemann surface, punctured Riemann surface. And the third piece of data is a glowing datum, right? Glowing these two things together. So this is going to be a G equivariant isomorphism. So between P G prime and PG prime prime, and this is going to take place on the analytic disk, which is punctured with X removed. So this notation here means X is removed. Okay, manuals. And this isomorphism takes place between PG and P prime and P prime prime, restricted to this punctured disk. They call this datum alpha, I guess. Right. So I think this is kind of transparent in the analytic situation. And so the point is that this can actually be formulated. A statement like this can be formulated to prove an algebraic geometry. We'll use it quite extensively. Okay, so to do this in algebraic geometry, just introduce a little bit of notation. So I'll write O subscript little x with a hat. This indicates the completed local ring of X at this point. So to be clear, I'm no longer assuming that K is the complex numbers and back in algebraic geometry. Kx hat, maybe I'll drop the hats at some point, but this is the fraction field of O hat. Okay. So this one is abstractly isomorphic to power series in a single variable, and this one is abstractly isomorphic to Laurent series in a single variable. And then I'll use the kind of inspired by the analytic situation, I'll use the following notation. So I'll write d sub x comma s for the spectrum of OX hat. Let's see, sorry, I don't want to write this. Let me write it as follows. So S is some test affine scheme as always, okay? And I can form the completed tensor product of the ring of functions on S with O hat. So again, this just means this is written as some limit, right? The limit of functions modulo powers of the maximal ideal, functions vanishing at x. And this completed tensor product just means form the tensor product of each of those finite dimensional quotients and then pass to the limit. So more explicitly, if I identify O hat with Laurent series, or sorry, power series in this case, this is going to be the ring of power series with coefficients no s, right? It's not the same thing as the abstract tensor product, right? This is an annoying thing that you have to deal with. And likewise for punctured disk, I do the same for the Laurent series ring. Okay, so again, it's this ring is the same as this ring, except I invert, right, the generator for the maximal ideal inside of here. Invert one tensor generator. You can also say, right, this is, and inspired by this, you can say this is dx comma s with the sort of center removed. Yeah. So it's important to make these definitions allowing for an arbitrary test scheme S, because that's how we make these definitions in algebraic geometry, right, by allowing families. And yeah, maybe to not belabor the point, you might have wondered why isn't this just like dx Cartesian product with S? No, it's not, exactly because of this completed tensor product, right? Because this is not the abstract tensor product, it's not just the product, the level of vacuum schemes, right? So it's just a slightly awkward thing you have to deal with when you're working with rings such as power series and Laurent series. So here's the theorem I was alluding to. It will be in Laszlo, or maybe they prove some special case, but it's essentially what I'm citing here. So G bundles, or even families of G bundles on X, I can write them in a completely analogous way to the analytic situation. So namely, I can write them as sort of triples. Okay, where this notation is exactly as in the analytic situation, right? So I specify a G bundle on dx comma s. This is a G bundle on x times s, sorry, x minus the point little x times s. All right, that for p prime prime lives, and this is an isomorphism over the punctured parameterized disk. So all this makes sense in algebraic geometry as well. And in fact, this the obvious map here, which is just restrict, if I have a G bundle on the entire curve, I can restrict it to the disk, I can restrict it to the complement of the point, and then over the punctured disk, these will be tautologically identified via the identity map. And the claim is that that is an isomorphism of groupoids. So this tells us we can actually, in algebraic geometry, specify G bundles by some kind of what's happening locally near the point X, and then what's happening everywhere else, and then identifying over the puncture disk. Okay. Questions about this? It's kind of a technical thing, but it's important.
Formal scheme or just spec?
Just spec, yeah. I mean, it's a good point. You can also consider formal spectrum split here, and that would be a different thing. And for some purposes, you do want to consider it. However, for this discussion, at some point you have to consider stack, because the problem is spoof maps to stack, right? It's kind of a subspace of stack. But if I take spoof and the formal spectrum and I remove the point little x, kind of imitating what I did here, if I took the formal spectrum and removed this point, I would actually get the empty suite. right? There'd sort of be nothing left. If I take like a non-reduced ring like the dual numbers and I remove the close point, I just get the empty scheme. So in order to do this process of removing the center, you really do have to work with the spectrum, even though from, it's very reasonable to say it's kind of a horrible object from the perspective of algebraic geometry, because I'm taking something like power series and thinking of it as an abstract ring. However, here it's something we have no choice. Yes, other questions? Okay, so got 15 more minutes, great. So I still need to talk about Hecke modifications. So I'm going to define another stack. So now the idea here, right, is because I can specify a G bundle in this manner, I can actually modify a G bundle using this kind of local description. Well, again, part of the data of the G bundle is this thing that's local near X. And then I have a bunch of what are called Hecke modifications at the point little x, I'll now describe. So these are some kind of local symmetries of the stack of G bundles, which are going to be very important in the Langlands program. Again, for the arithmetically inclined, this is all kind of imitating the theory of Hecke operators in modular forms somehow. So my notation will be H, script H, G, comma little x. This is going to be, I'll write the name and then I'll define it. Stack of Hecke modifications. Yeah. And here's the definition. So I need to, as always, specify what it means to give an S point for a test scheme S. And it's going to be the following. So it's going to consist of a triple. And what notation do I want to use? I think, yeah, in order to avoid confusion with the notations I was using over here, I'll just use something slightly different. So I'll do P1 and P2. I'll still use alpha, I think it's okay. And here, P1 and P2 are the same kind of thing. They're both going to be G bundles on the disk, randomized disk. And alpha will be an identification between them over the punctured disk. Okay. So this is, again, some abstract stack. I think, have just barely enough time to say a few words about, like, what does it actually look like as an algebra of geometric objects, similarly how I did for Bun G. Let me postpone that for a minute and say, it's not just an abstract stack, it also has another structure. Namely, I can sort of compose such triples. So, in fact, this is a groupoid. And a groupoid, I mean, it's like a category, right? It's kind of objects and it has morphisms. So I have to specify sort of what is the space of objects of this thing, right? So there's some base that it has to live over, and it's a groupoid over the moduli of G bundles on the disk. So hopefully this notation is kind of clear what I mean, right? And what I mean is that I can sort of compose the alphas. Right? So if I have two such triples, like P1, P2 alpha, and then say the fact that this is going to take place over Bun GD means that I have a second triple that's like P2, P3 beta, then I can write a triple P1, P3 beta compose alpha, right? Compose them. Okay, so it has this kind of structure.
Are you going to define each equal x itself, or?
I just did it.
But this is the massive right?
Exactly. I specified as a number. Like I said, I'll say what kind of an algebraic geometric But I didn't make any points about what's. Yeah. And so, Bobby Laszlo tells us that this groupoid, in fact, acts on Bun G, kind of over Bun G on the disk, in the sense of a groupoid acting on a space, over some space over the same base. So again, think about it, there's only kind of one way to interpret what this means. So like if I have one of these triples, right? And I also have a G bundle on the entire global curve, right? And the sort of second, the P2, right, in H agrees with the P prime, right, in my Bobby-Laszlo datum, right? Then I can amalgamate these, right? Basically replace P prime and P2 are the same thing here because of this fiber product. And so I replace P2 by P1 using the second modification, using the alpha there. And this gives me another G bundle. So this is the action map for this action. Okay, so this is kind of like the key sort of local structure on Bun G that, as I say, it's telling us that Bun G has some symmetries that are of a local nature. Clearly, this HDX, like everything I said there, is taking place kind of on a formal disk around the point, little x. Yeah, I have 10 minutes left. So let me go back and do what I promised, which is to say what kind of an object, algebra geometric object this H is. I'll explain what it is a little more explicitly, and that should be helpful for various reasons. Uniformization. Uniformization to me, I don't know what it means to you, but to me it means like writing a stack as a global quotient or something like that, like writing it as something, not something else. In some sense, every stack is sort of somehow locally looks like a quotient or something, but you, in many cases, would like to write it as a global quotient. So that's what I'll do for H. Okay, so this requires introducing another character, again of a local nature. So it'll be script L sub little x of G. This is, okay, again, I'll name it and then I'll write the definition. So this is the loop group of G, kind of loops based at X, something like that. Not based, but okay. I'll write the definition in a moment. This has a subgroup, which we write as L plus. It's called the arc group. And now I'll say what the points of these things are, again, by specifying maps into them, but then I'll say what kind of an object it is. So I'll talk about representability. In fact, I guess I could just squeeze it in here. So an S point of the loop group is a map from this parameterized disk into G. And likewise, puncture disk. First it's the loop group, and then for the arc group, it'll be the same but non-punctured. Okay. And now representability, well, it's not literally representable, it's not a scheme. Neither, well, so the loop group is not a scheme, the arc group is. And The loop group itself is sort of the more exotic kind of object, so it's in affine in group scheme. Sorry, group in scheme. Should be careful when I say that, right? So I'll say what I mean. Okay, so this is some algebra geometric mumbo jumbo. So first of all, what do I mean? The R group is an affine group scheme. I didn't say algebraic group for a reason, because it is of infinite type, right? So if I consider maps out of the disk, well, this sort of the disk is the Laurent series are a limit of all the truncated polynomial rings of all degrees. If I were to take maps just out of spec of polynomials mod t to the n, that would in fact be a fine dimensional algebraic group. But when I consider the entire disk, right, I am actually, this thing is a limit of algebraic groups of finite type. And so it's this type of thing, it's infinite type. For LXG, for the loop group, it contains the art group as a subgroup, and it's sort of the loops which extends to a map out of the disk. And then I can consider loops which kind of have a whole of order 1 and order 2 and order 3 and so on. And so, in fact, if I bound the order, each of those will be sub-schemes, but not subgroups, right, which are themselves affine. And in this way, you write the loop group as a union of affine schemes with the transition maps being closed embeddings of finite representation. So this is the kind of thing that it is. And it's infinite type, but somehow this is like, as far as infinite type goes, this is one of the more manageable kinds of things, because you can describe it in terms of limits and colimits in the way that I said. And so here's sort of the key observation for this uniformization. So locally on the test scheme S, any G bundle on the parameterized disk actually descends to S. So what I mean is if I have a G bundle on the parameterized disk, I can replace space change along some ATOL covering of S to some S prime, say, and then after doing this, the G bundle will actually descend to S prime. Okay? The way you prove this is you actually use this formal spectrum that was alluded to earlier. You can prove that because G is affine, G bundles on stack are the same as G bundles on split, and then you use the fact that G is smooth to show that, in fact, you have a section. If you definitely have a section locally on S, kind of by definition, and then you can extend that to a section over the entire formal disk using formal smoothness. So that's kind of just a sketch of how you prove this local triviality. And so the upshot of this is this stack that I wrote earlier, Bun G on the disk, is actually just a classifying stack of the arc group. That's kind of precisely, certainly inside of here, you have the trivial bundle, and it has automorphism group arcs into G. And what I just said implies that, that's the only data point. So what does this tell us about the first, let me say, what does it tell us about G bundles on loops? So the same is true for G bundles on the punctured disk, and there's a small caveat here of technical nature, which is that I have to say it's true for G bundles which admit some extension to the entire disk. Technically, in general, there are some G bundles that don't extend, and you don't want to think about this, trust me. So you only consider the ones that extend, and then tautologically, right, if they extend, then they descend locally on S. And so then what that tells us is that the Hecke stack, so by definition, right, this is the fiber product Bun G on the disk, fiber product with Bun G on the puncture disk. This is this fiber product by definition, right? That was the definition I wrote exactly. And this, because of the previous board, right, this is a fiber product of classifying stacks. And the base here I can replace by the classifying stack of the loop group, because by definition in this fiber product, I'm only considering G bundles that extend, right? Okay, and then tautologically, if you take a fiber product of classifying stacks, right, or of classifying stacks of this form, you exactly get the double coset space. This is just a general thing about group lengths or whatever. This double coset space is also a groupoid. This is, in fact, an isomorphism of groupoids. So this gives some description of H as a global quotient. I'm out of time. Can I take like 2 more minutes? Is it? No, it's we're very short in time. Okay, 2 more minutes just to say. I didn't yet say what the affine grassmannian is, and that's kind of important. Okay, so one thing I can do, right, is this is this double quotient. It's a stack, but I can also just take the quotient on one side. So this gives me what's called the affine grassmannian. Of G at the point X. By definition, it's this quotient. And for lack of time, I won't write the moduli space description, but you can very easily work out what it is, right? It's a G bundle on the disk together with trivialization on the materials, right? And so then you see that this Hecke stack, oh, and sorry, before I say that, this thing is a quotient of this this group in scheme by this sub scheme. And in fact, you can show that this is a int proper in scheme. So what you should think is that somehow this quotient is analogous to the quotient of a finite dimensional reductive group by a parabolic subgroup, really by a maximal parabolic subgroup, hence the name, right? If you take a quotient of GLN by a maximal parabolic subgroup, you get a classical Grassmannian. This is some infinite type analog of this. And like the classical Grassmannian, it's kind of projective, in this case, int projective, because it's infinite dimensional. But nonetheless, importantly, as part of proper, this means it's written as a union of projective varieties along closed embeddings. And in particular, those are finite type, right? Those are like finite type projective varieties. So this thing is infinite type. This thing is also infinite type, but somehow this quotient kind of cancels out the infinite typeness, and you get a union of finite type things. And then finally, of course, I can write the Hecke stack like this, which is kind of an important presentation. But this sort of tells you what is this thing? This is some proper in scheme, and then I'm quotienting by some affine group scheme. And so I've written it as some kind of global quotient stack. This thing is infinite type, so maybe that causes a small amount of headache, but this is a very useful presentation. All right, I'll stop there. And this is other questions.
Questions to the press, but please feel free to
Come to the judge and ask him